Welcome to this deep dive into deep reinforcement learning. We'll explore the mathematical foundations and advanced techniques that drive this fascinating field. Prepare to engage with complex equations and concepts that underpin modern AI advancements. Our journey begins with an overview of deep reinforcement learning. We'll cover value-based methods like deep Q networks and policy-based approaches, including policy gradient methods and actor-critic frameworks. In tabular reinforcement learning, Q-learning updates the Q value using the Bellman equation. However, large state action spaces, like those in Atari games, pose significant challenges due to their vast size. To generalize across states, we approximate the Q function using a neural network. This approach allows us to handle unseen states and actions efficiently, reducing the need for extensive storage. Feature engineering can be crucial in reinforcement learning. For instance, in Tetris, handcrafted features help approximate the Q function. However, deep neural networks can automate feature learning across tasks. Deep reinforcement learning leverages deep neural networks to represent value functions and policies. This approach is effective in both discrete and continuous action spaces, as seen in models like DQN and DDPG. The Deep Q network, DQN, uses a neural network to approximate the Q function. However, naive implementations can diverge due to correlated samples and non-stationary targets. Experience Replay stabilizes DQN training by storing transitions in a replay memory. By sampling mini-batches, it breaks the correlation between samples, adhering to the IID assumption. The delayed target network technique further stabilizes DQN. By using a separate target network, it prevents the Q value targets from shifting too rapidly during training. Optimization techniques are vital in deep reinforcement learning. Reward clipping and RMS prop can improve gradient conditioning, while batch normalization helps stabilize training. In Atari games, DQN processes raw pixel inputs through convolutional neural networks. This end-to-end approach outputs Q values for each action, demonstrating the power of deep learning in complex environments. Double DQN addresses the overestimation bias in Q-learning by decoupling action selection and evaluation. This method uses two networks to provide more accurate Q value estimates. Prioritized replay enhances learning by sampling transitions based on their surprise value. This approach focuses on more informative samples, improving the efficiency of the learning process. The dueling network architecture separates the value and advantage functions. This separation allows for more robust learning, especially in environments with varying state importance. Policy-based methods use neural networks to directly approximate policies. This approach is particularly useful in continuous action spaces, where traditional value-based methods struggle. The Deep Deterministic Policy Gradient, DDPG algorithm, combines Q-learning with deterministic policy gradients. It excels in continuous control tasks by optimizing policies directly. Episodic policy gradient methods optimize stochastic policies by adjusting the probability of action sequences. This approach focuses on maximizing expected rewards over entire episodes. Variance reduction techniques, such as using baselines, help stabilize policy gradient methods. By reducing variance, these techniques improve the reliability of gradient estimates. Actor-critic methods use function approximations to estimate both the policy and value functions. This dual approach balances bias and variance, enhancing learning stability. The Asynchronous Advantage Actor-Critic, A3C algorithm, uses parallel workers to stabilize training. This method is an alternative to Experience Replay, offering robust performance in complex tasks. Generalized Advantage Estimation, GAE, provides a trade-off between bias and variance. By adjusting the advantage estimation, it enhances the efficiency of policy optimization. Policy optimization methods directly optimize policies, offering flexibility across tasks. In contrast, value iteration methods exploit Bellman equations, providing sample efficiency in stable settings. Thank you for joining this exploration of deep reinforcement learning. We've covered foundational concepts and advanced techniques, equipping you with the knowledge to delve deeper into this dynamic field.